Today we're reviewing chapter 6 for the most part, which means we are reviewing the fundamental theorem of calculus. Our book labels it part 2. In our textbook, part 1 is how do you do integrals? Integral of little f from a to b, figure out an antiderivative, capital F, do capital F of b minus capital F of a. How to evaluate definite integrals. Part 2 in chapter 6 kind of goes the other way around. Instead of using an antiderivative to compute an integral, we're using an integral to compute an antiderivative, to construct mathematically an antiderivative. Though, if you're really going to apply it in significant ways, you've got to do numerical integration. But as a theoretical idea, it's still important. FTC part 2, how does it go? It starts like this. Suppose little f is a nice function. What does nice mean for us? Typically with integrals, nice means continuous. Not necessarily differentiable. That would be nicer. But usually continuity is good enough for saying what we're about to say. So it's continuous on a closed interval from a to b. We're going to define a new function, suggestively called capital F. Why? Because it's going to be an antiderivative. Capital F on the interval from a to b. Sorry, I was going to write the formula for capital F there, so I sort of put it down a little bit, but hopefully this is not bothering you that I put it downwards there a little bit. By the formula capital F of x equals the integral of little f. Got to be careful about my notation here. My lower limit of integration, I'm going to pick to be a, which is the left endpoint where little f is continuous. But realize I actually could pick the lower limit of the integration to be any number between a and b. And the upper limit of integration, I'm going to make be the variable x. So these variables here and here need to match. And they do. Now, sometimes we're sloppy in math class and it's okay. Like when I write something like y equals y of x, that's technically sloppy math. That's abuse of notation, it's called. Not abusing notation, but abuse of notation. Not abusive, but abuse of. We are abusing notation, meaning we're using the same letter y to represent both a dependent variable, a number, and a function name. We're mostly, for the most part, okay with that kind of sloppiness. It's just so traditional. However, there's some kind of sloppiness we're not okay with. I am not okay with you putting x there. I want you to use some other letter. Don't use an x for sure. I guess we better not use an a or an f either, because those are already being used. How about our old friend from substitution, w? Yeah, that's fine. In this context, w is called a dummy variable. Why? Because it just doesn't mean anything. I mean, it's kind of silly. In reality, you could call all variables dummy variables because they don't mean much beyond just representing a number. But it's best, and I want you to use a different letter there. Make sure the variable here matches the variable there. This is a formula that defines a new function. If this is the graph of my little f, like this is the little f. Maybe this axis is labeled with a w. And x is any number between a and b. Let me pick it to be, say, right there. That's x. I can, theoretically at least, compute this integral. Although since this is the second part of the FTC, we would actually not use the first part of the FTC to do it. In reality, we would approximate the integral with numerical integration to be this area minus this area. And that would be the value of capital F of X at that value of X. But for different values of X, we'd get different areas. This is a function of X. The conclusion of this theorem, then the derivative of capital F of X is little f of X. Capital F is an antiderivative of little f for all X in the interval. We have constructed an antiderivative of little f. It's very important here that these variables match too. Before, the variable for little f was labeled W. But now, since I'm labeling the variable for capital F prime as X, I want the same variable name there. Do not change it back to W. Don't keep it to be the W there, or the T, or whatever letter it is to start with. These have to match. That's very important. Another way to write this last fact is with ddx notation. In this context, if we take the derivative with respect to x of the integral where a is the lower limit and x is the upper limit of little f of w dw, we get little f of x, not w. These x's all need to match. Again, the w doesn't matter. I can use a t, I could use a u, I could use a z, I could use a Greek letter. It doesn't matter. You want to emphasize the upper limit is the variable. What if I tried to graph capital F? What would it look like over the same interval from A to B? One thing to notice is that since the lower limit of this integral, defining capital F up here, is A, that would also mean capital F of A is the integral from A to A of little f of w dw, and the integral from A to A by definition is 0. Capital F of A is 0. That's an x-intercept. I'm going to label this axis with an x. Don't let that bother you that I change the label. That's my variable for capital F. It's an antiderivative of little f. If you differentiate the graph I'm about to draw, I have to get little f. Going backwards, if I start with little f, notice at x equals a, the slope is positive. The value of little f is positive, so the slope of capital F is positive. And in fact, the value of little f is going up, so the slope of capital F has to be going up. It's got to be concave up. Until you get to this maximum point for little f, that's where that'll be an inflection point for capital F, right about there. And then when little f is 0, the antiderivative will have a 0 slope. This graph up here at the top gives you slopes of the graph at the bottom. Then a negative slope in here, most negative right about here, another inflection point. Back to 0 slope right here before going back to positive slope in here from A to B. Let's pretend B is more like right there. Okay, not a perfect drawing. Get the idea. This is a capital F. In reality, if we're going to, partially what this theorem is for is assuring us, yes, we will have an antiderivative. And partially by thinking about this graphically, it reminds us that to approximate values of this antiderivative, we need to do integrals, meaning we need to do numerical integration. We need to approximate it. Because if we could use the FTC part 1 to do integrals, there'd be no need to use FTC part 2. Kind of weird, but true. All right, what I'm going to do next is talk about an application of this, an important kind of application. Then I'm also going to talk about typical kinds of homework problems you'll see in section 6.4, which could also show up on Wednesday's mini exam. But let's talk about why this is important. I want to talk about statistics. Something called, in particular, the standard normal distribution. This is the most important function in statistics. What is its formula? F of x equals 1 over, this is kind of weird, square root of 2 pi times e to the negative x squared over 2. That is the formula for the standard normal distribution. What does its graph look like? It is a bell-shaped curve. You could call it even the standard bell-shaped curve. It's got a maximum value at 0. It's an even function. It's got symmetry with respect to the vertical axis. You can see that here. It also turns out to have inflection points at 1 and negative 1 are a couple inflection points. And most important, most amazing of all is that the total area under the curve equals 1. And when I say the total area under the curve, I mean a region that's shaded red here that goes to the left and right forever and ever. Of course, only in your imagination. Forever and ever. It's an infinite extent region, but that infinite extent region amazingly has finite area of exactly 1. Kind of weird, but true. By the way, that would mean that if I did not have the 1 over square root of 2 pi here, if it were just that function right there, then the total area under the curve evidently would be square root of 2 pi. Somehow this function relates e and pi. Mysterious. Why? Well, you'll find out if you take multivariable calculus. But we can confirm it. That's third semester, Calc 3. We can confirm it with Mathematica. Actually, if you want to confirm that this is the right formula for the standard normal distribution, you use a command called PDF, which stands for probability density function. Let me go ahead and write that out. This is a probability density function, or PDF for short, also known as PDF, is analogous to a mass density, but let me not go into that at the moment. To see that it's the right formula, I also want to put in square brackets here normal distribution. And then square brackets 0, 1, then another comma after that, x is the syntax. Normal distribution 0, 1 stands for this distribution. Centered at 0, that's the so-called mean in statistics, with a standard deviation in statistics of 1. It's a measure of the spread, how spread out this is. And then the PDF tells you the formula as a function of x here ultimately. And we'll see it's the same formula. There it is. Let me go ahead and define this to be a function, f of x. So I'll copy and paste this. Enter it. It is now entered. I can see it here if I type that. That's our standard normal distribution, PDF. Okay, why do I care about this? What's the relevance? You use PDFs, whether they be a standard normal distribution or something else, to find probabilities, likelihoods of variables being in certain ranges of values. Common notation is to use the letter P for probability. And then the range of values you're talking about might go from some number A to some number B. You might write that like this. It's somewhat traditional to use a capital X in here, so I will do so, but the A and B are lowercase. This whole symbol represents one number, the probability that my variable is between A and B. And the idea is that you find this probability by integrating. And the reason you want the total area under the graph to be 1 is because the probability of something happening should be 100%. Your variable's got to take on some value for sure. 100% chance. Probability 1. That's why we want the area under this to be 1. And this is the importance of this probability density function, is it can be used to compute probabilities. I can have Mathematica confirm also that this does give us a probability of 1 by integrating it, but not over a finite interval, but instead from -infinity to infinity and beyond gives you an answer of 1. It is a probability density function when that happens, when the area under it is 1 and when it's also not negative, because probabilities can't be negative. How is that done? Well, first of all, that's an improper integral. The limits of integration are plus or minus infinity. We haven't done that before. But you can define what this means. It's, guess what? Limits come into play in defining this in the first place. How do you do it, though? How would you find that value of 1? Again, it takes multivariable calculus. Can Mathematica find an antiderivative of little f? Yes and no. Yes, it's going to give me an answer, but no, it's not an answer you've ever seen before. It's ERF. Does that 1/2 ERF of x over square root of x, does that mean somebody had a last name of ERF? No. ERF stands for error function. And the reason it's called the error function is because normal distributions like this, bell-shaped curves, are applied all the time to model errors in experiments, whether they be measurement errors or random errors, noise, that kind of thing. Normal distributions are used to model those kinds of things. Actually, it's better for noise, randomness. Measurement error, it's a little bit trickier because you can have some consistently, your measurement errors could be biased in one direction. You could be consistently measuring something too large, for example, larger than it's supposed to be, whether that's a mass or a length or whatever. So the integral of this does exist, but it's not a function you're used to, but it does exist. There is an antiderivative of little f. And we could use that antiderivative, if we had it, to compute f of b minus f of a, to do the integral. The cumulative distribution function, or CDF, turns out to be one particular antiderivative. CDF for short. It's not any old antiderivative, it's one particular one. For the sake of, just in case you ever see this in the future, and partially just because I like Greek letters, I'm going to show you its official name. Well, first of all, what does it represent? It represents the probability of the variable being less than or equal to little x. It's called this capital letter is called a random variable. And little x is an arbitrary number. The notation for this is a Greek letter, capital phi of x. Kind of looks like a squishy thing that you might see in Mario Brothers or something. Capital phi. Mathematicians almost always call this phi. Physicists almost always call this phi. Don't call it full or fun, though. I asked a Greek professor, is it phi or is it phi, to try to resolve the issue, and the Greek professor said it's either one. Okay. You could call it phi, you could call it phi. I like to say phi because all my mathematician professors called it phi. It's this probability, which is the integral from minus infinity to x of the PDF. I'm going to use a different letter here because my variable is in the upper limit of the integral, like w. Actually, in this context, it's the most common letter to use is actually z instead of x or w. Z is the standard letter to use for standard normal distribution, but we don't have to worry about that. Okay, so is that ERF function that we saw equal to this? No. So what is it if it's not? Let's plot both the original f of x and this error function, 1/2 ERF of x over square root of 2, say x going between -4 and 4 or something. Plot them both. What do we see? Actually, let's see. So f of x is that thing. Okay. Something's not, okay. Yeah, something's not looking right. It's not the CDF. What do we see here? We do see the blue graph, that's the little f, and the gold colored graph, that's this ERF function. It's not the CDF, however. Why not? Because look, it goes negative. Probabilities can't be negative. That's one reason it can't be the ERF function. Can I modify it to make it? It can't be the CDF. Can I modify it to make it the CDF? Yeah, it turns out I can add a half to it. Now it's never negative. And moreover, as little x goes to infinity, capital phi goes to 1. Look at those outputs are getting closer and closer to 1. We're getting closer to including all the probability for all the possible values of x. On the other hand, as x goes to minus infinity, the output goes to 0. By adding 0.5 to it, I have made this now a formula for the CDF. The 0.5 is effectively taking into account the fact that this graph is symmetric and the area over here is 0.5. The plain old ERF function by itself goes through the origin. By adding on that 0.5, I have made it equal to this function here. And I didn't have to type in an infinity anymore. So what's the value of all this? The value is knowing that in creating this function, we have created an antiderivative of little f. FTC part 2 tells us that the derivative of capital phi is little f of x. I've created an antiderivative. You can tell graphically that that's the case. The derivative of the gold graph is the blue graph, which does turn out to be important in many applications. That does turn out to be important in many applications. If I didn't know the answer was this ERF function, what could I do instead? I could, whoops, not do that. Go down here. I could define capital F, the CDF, if I called it a different letter, like capital F, using numerical integration. Quickest way to do that is with n integrate. Avoiding summations. We're not doing a left-hand sum or a right-hand sum or a trapezoid sum here. We're doing something better, more accurate, and quicker. We're using something built into Mathematica to approximate areas and integrate. The n stands for numerical approximation. The little f of w, say w goes from 0 to x, and then I'll also add on the plus 0.5. This is integrating from 0 to x, giving me an area between 0 and x. Adding on the 0.5 gives me the area to the left of 0, the total area to the left of x when I combine these things by adding them. This function is going to have the same values, for example, at x equals 1, as this function will. I must have deleted that plus 0.5 here. This function will have the same value at x equals 1 as well. If I replace x with 1, I get the same answer. Same thing will happen if I replace x with any value. So again, for emphasis, ERF is the name of the function in Mathematica, and more generally, people call it error function. They might not always call it ERF. It is an antiderivative. Not elementary function, though, not a function you're used to. It's a new kind of function. To program Mathematica or your calculator to approximate its values, you've got to do numerical integration. Done quickly here with Mathematica, using this kind of code here. But the equality of these things is illustrating that it is doing the right thing. And I could then use capital B, the CDF, as an alternative way of doing this. Because of this, I could do capital phi of B minus capital phi of A. Capital F represented any antiderivative. Capital phi is one particular antiderivative that's especially useful in interpreting probabilities. So all that is to say, this is an application of the second fundamental theorem of calculus, and a very important application. I'm just hinting at how it's related. It's got lots of consequences that are important in statistical modeling. But what about using the second fundamental theorem of calculus to do a homework problem from section 6.4 of the type you should practice a little bit before Wednesday's mini exam? So I'm about to show you a tricky kind of problem you will find in section 6.4 and also in my solution key to the review problems at the end of chapter 6, which many of you don't have in your book. You should be able to do what I'm about to show you, but it's tricky. What is the derivative with respect to x of, for example, the integral from 0 to, say, x squared of cosine of t cubed, say? I'm using a t now instead of a w. It's not a big deal. That's more consistent with the homework problems in section 6.4. But notice I made this upper limit of the integral x squared instead of x. A little extra wrinkle. What's the purpose of this? Purpose is just practice with derivative rules, including this second fundamental theorem of calculus and a rule from earlier in the book. Calc 1, what's one of our more famous rules? It starts with a C and then an R. Chain rule is part of what we need here because x squared is the inside function. When you plug in a number for x, what do you do first? You square it first before doing this integral. This entire expression here could be thought of as a function composition, call it capital F of g of x, where capital F of x is the same integral, except you make the top limit of integration just a plain old x instead of an x squared, and g of x is that inside function x squared. FTC part 2 says that the derivative of capital F is cosine of x cubed. Make sure these x's match. Ignore the fact that that's a t there. It doesn't matter. These variables should match. That is important to not be sloppy here. I also know that the derivative of g is 2x. By the chain rule, written first in its abstract form, this derivative is capital F prime of g of x times g prime of x, the derivative of the outside function, capital F, plug in the inside function g, then multiply times the derivative of the inside function, multiply by g prime. And I already have these things. I know what these functions are. Use them now. Capital F prime, you can see, capital F prime of x is cosine of x cubed, but, I'm plugging g into there. I'm combining those two things. I'm replacing, in this formula here, the x with x squared, meaning I have to do x squared cubed. Then times g prime of x times the derivative of the inside function is times 2x. The derivative of x squared is 2x. Simplifying, it looks like the answer is 2x cosine of, you'd multiply those exponents, 2 times 3 is 6. 2x cosine of x to the 6th. Is it right? Did we make a mistake? It is right. I checked this in the first class. How could we check to see if it's right? We might do something else. We might see if we can use this to figure out maybe the first positive critical point of this function here. Let me give this function another name. Let me call it h of x. We have just found h prime of x. I might like to know where the first positive critical point of h is to help me graph it if I wanted to by hand. How do you find critical points? Take the derivative, which we've already done, set it equal to 0, solve for x, right? Optimization. Set h prime of x equal to 0. That's going to mean 2x cos x to the 6th is 0. That does have one solution at x equals 0, but guess what? 0 is not positive. 0 is not greater than 0, so that doesn't count. I want first positive solution. So essentially, I just ignore the x and focus on the cosine. The first positive input to the cosine that will give you 0 for output is pi over 2, 90 degrees. Cosine of 90 degrees is 0. Cosine of pi over 2 radians is 0. This means we always use radians unless told otherwise. X to the 6th must be pi over 2. And so x itself must be pi over 2 to the 1/6 power. I'll use my calculator to approximate that. Pi divided by 2. About 1.57. Raise that to the 1/6 power. It's about 1.08. Is that right? Is it the first positive critical point? Let's have Mathematica check it. Let's plot. The original function h of x, so I really should use n integrate to help me define h of x. N integrate. What was it? Go back to the original formula. H of x is this thing. Cosine of t cubed, t going from 0 to not x, but x squared. Let's plot h of x, say from 0 to 1.5, and see if it looks like the first positive critical point occurs at about 1.08. Let's see if that happens. Takes a while to plot because it's doing a lot of calculations. There we go, though. That's the graph of the h of x function. Yes. When x is about 1.08, that's where the first positive critical point is. It's a local maximum. Could we also confirm it numerically? Yeah, you could do something like this. Find root. I have to use find root because it's a numerical approximation scheme. Give it a guess like 1.08. We already know the answer. Yes, that 1.07817 that you see there is in fact the same thing we got with the calculator, 1.07817. We did do it right. So it's a little tricky. It takes practice. Don't study for Wednesday's exam without practicing this kind of thing. You'll find it in section 6.4.